Hello everyone. Today I would like to cover one derivation which is on numerical aperture of optical fiber. And this derivation is asked in Mumbai University in the subject Engineering Physics 2 and RTM Nagpur University Electronics and Telecommunication. They are having a subject optical communication. This question is asked for 7 marks. And the question is derive an expression of numerical aperture for a step index fiber. In this question, we have to derive an expression of numerical aperture for a step index fiber. Now we will see this derivation. Numerical aperture of optical fiber. Now this is an optical fiber, and this is the outer part is your cladding, and inner part is the core, and this is core axis. Now air is entered into this at point A into core, and air is having a refractive index of n0 and core is having a refractive index of n1. As the refractive index changes, therefore this ray will change its direction or angle. This ray entered at point A with an angle of theta A. Then after entering into the core, it will make an angle of theta R, and then it strikes at core cladding interface, and after that it will refract into the core medium. Now core is having refractive index of n1 and cladding is having a refractive index of n2. You have to remember that the refractive index of core is always greater than the refractive index of cladding. It means that n1 is always greater than n2. Now first of all we will apply Snell's law at point A, that is air core interface. Snell's law is always applied at two interface, means it is air core interface, or we can also apply Snell's law at core cladding interface. In this derivation we will be applying Snell's law at air core interface and then core cladding interface. First of all, applying Snell's law at point A. Now, as we know that air is having refractive index of n0 and core is having refractive index of n1. So in Snell's law we have to multiply the refractive index of the medium into the angle at which the ray is incident, means n0 sin theta A is equals to n1 sin theta r. n0 sin theta A is equals to n1 sin theta r, and sin theta r is nothing but, now here as we can see, this is angle 90, this is 90, and this is theta c. Therefore this angle is 90 minus theta c, and these two angles are same. Theta r and this 90 minus theta c are same angle. Therefore theta r is nothing but 90 minus theta c. So we are replacing theta r by 90 minus theta c. As we know that sin 90 minus theta is always a cos theta. Therefore n0 sin theta A is equals to n1 sin theta c. Therefore sin theta A is equals to n1 upon n0 cos theta c. Give it as equation number 1. As per our trigonometric formula, we know that sin square theta plus cos square theta is equals to 1, and cos square theta is equals to 1 minus sin square theta. Now here, as it is cos theta c, so we are interested in cos theta c, so taking under root on both the sides. So under root of cos square theta is cos square theta is equals to under root of 1 minus sin square theta c. Now here it is theta c, so here I have written theta c. Therefore cos theta c is equals to under root of 1 minus sin square theta c. Give it as equation number 2. Now substituting equation number 2 into equation number 1. Here we are substituting equation number 2 into equation number 1. Therefore sin theta A is equals to n1 upon n0 under root of cos theta c. Cos theta c is nothing but under root of 1 minus sin square theta c. So here we are replacing cos theta c by under root of 1 minus sin square theta c. Give it as equation number 3. Now the next step is applying Snell's law at point B. Now here also we are considering two interfaces. One is core and other is cladding. So it is n1 sin theta c is equals to n2. Here the angle is 90, therefore sin 90. Here we are considering this ray, therefore we have to consider this angle. So n1 sin theta c is equals to n2 sin 90. Next step is applying Snell's law at point B. So n1 sin theta c is equals to n2 sin 90. As we know that sin 90 is always 1. Therefore it is n1 sin theta c is equals to n2. Therefore sin theta c is n2 by n1. Give it as equation number 4. Now substituting equation number 4 into equation number 3. Now equation number 3 is sin theta a is equals to n1 by n0 under root of 1 minus sin square theta c. Here we are replacing sin square theta c by n2 by n1. Therefore sin theta a is equals to n1 upon n0 under root of 1 minus n2 by n1 the whole square. As we know that sin theta c is n2 by n1. Therefore we are replacing n2 by n1 the whole square. So it becomes under root of 1 minus n2 square upon n1 square. So we are cross multiplying it. After cross multiplication we will get n1 by n0 under root of n1 square minus n2 square upon n1 square. We are taking n1 square outside the under root. Therefore it is n1. n1 will get cancelled under root of n1 square minus n2 square. Therefore it is 1 upon n0 under root of n1 square minus n2 square. As we know that air refractive index is, the value of air refractive index n0 is always 1. Therefore this n0 is 1. So sin theta a is equals to under root of n1 square minus n2 square. Sin theta a is equals to under root of n1 square minus n2 square. This is nothing but your numerical aperture. Therefore numerical aperture is equals to sin theta a equals to under root of n1 square minus n2 square. I hope you have understood this derivation. Thank you.